Factors on which resistance depends. It has been seen experimentally that if the length of a conductor is doubled, all other dimensions remaining the same, the resistance is also doubled. It has also been observed that when the cross-section area of a conductor is doubled, the resistance of the new conductor is halved. This implies that electrical resistance is directly proportional to the length of the conductor. This also implies that electrical resistance is inversely proportional to the cross-section area of the conductor. Putting these relationships into a single equation, we see that R is proportional to L upon A, where L is the length of the conductor and A is the cross-section area. Introducing a constant of proportionality into this expression, which we will call rho, we get R is equal to rho multiplied by L upon A. The constant of proportionality is denoted by the Greek letter rho and is called the specific resistance or the resistivity of the conductor. Please note, this is an intrinsic quality of the conductor as it is completely independent of the physical shape or size of the conductor. Its unit is ohm meter. Metals and alloys tend to have very low resistivities, generally in the range of 10 to the power -8 to 10 to the power -6 ohm meter. Insulators on the other end of the scale are characterized by extremely high resistivities, often in excess of 10 to the power 16 ohm meters. Electrical heating devices which use metal alloys of relatively high resistivity, like nichrome, require high resistance to produce heat. In ohmic conductors like metals, higher current causes higher power dissipation and thus a greater output of heat. So let us look at this concept in a bit more detail. Let us say that we have a bar of copper which has a length of 1 meter and a resistance of 20 ohms. What will happen if I were to increase the length of this bar by the factor of 2? In other words, what would happen to the resistance of this bar if I increased it to twice its previous value? If we look at the equation that we studied earlier, we understand that doubling the length of this bar will double the resistance to twice its previous value, as you can see. If I were to ask what will be the resistivity of this new bar of copper, the answer is the resistivity would remain exactly the same. Remember, resistivity is a property of the material itself. It is not affected by the physical shape or structure of this material.